Hello, this is Professor Kuehn. We've been looking at the work of John Tyndall, his lectures on light. We've gotten to about page 262 in a Student's Guide to the Great Physics Text, Volume 3. Last time we left off with the discussion of the total polarization of light upon reflection. You might remember we were talking about the experiments of Malus. Malus had discovered in 1808, by observing light reflecting off some of the palace windows at Luxemborg Palace in Paris, that at a particular angle, the light is completely polarized when reflected off of this surface. Now, this wasn't a systematic study. It was Sir David Brewster who did a more systematic study of the polarization of light by reflection. So I'd like to say a few things more about that. There's a small paragraph. It's the second full paragraph on page 262. I'll go ahead and read this, and then I want to work out a problem and show the implications of this. So it says there that Sir David Brewster proved the angle of polarization of a medium to be that particular angle at which the refracted and reflected rays enclose a right angle. The polarizing angle augments with the index of refraction. For water, it is 52½ degrees. For glass, as already stated, 58 degrees, while for a diamond, it is 68 degrees. So what is he saying here? I'm going to draw a piece of material. This is the surface of, let's say, a glass block or a piece of diamond or something like that. And let's suppose that we have a ray of light coming in to this glass block and reflecting off of it. Of course, as you know, when light, so coming in like this and reflecting off, and as you know, when light is incident on a surface, some of it will be reflected and some of it will be transmitted. And normally, according to Snell's law, the incidence angle is exactly equal to the reflected angle. And as you might imagine, the refracted ray, if it slows down, is going to be bent a little bit more like that. And so we have here, I'll call that theta refracted. Okay. And I'll draw arrows representing that this is the incoming ray, this is the reflected ray, incoming, reflected, and of course the refracted ray. Now, what is he saying? He's saying here that if you fire this light in at a particular incidence angle such that the angle between the reflected and the refracted ray happens to be 90 degrees, that is the condition such that there is total polarization of the reflected ray. So let me redo this drawing. I'm going to change the angle of incidence so that it fulfills this condition. Okay, so let's suppose that we have this refracted, I'm going to try to draw it like this. So a reflected ray like this, and the refracted ray, and these happen to make a 90-degree angle. So this is the reflected ray, and this is the refracted ray. And in order to do this, let me see, I'm going to try to draw the incoming ray like this. Okay, the incoming ray and the reflected ray, and of course, as always, the angle of incidence is equal to the angle of reflection, and this would be the angle of refraction. I'm going to draw once again a capital R for the refraction, but now we have the coincidence, or the particular case where there's a 90-degree angle between the reflected and the refracted. And this situation is the case of total polarization of the reflected beam. So in other words, I'm going to try to draw polarization. So in other words, if the incoming ray had polarization that was vibrating in this direction and also into and out of the page, it's going to be hard for me to draw that, but this circle represents vibration into and out of the page. In other words, there's both transverse polarizations. Then the reflected ray only has polarization that is perpendicular to this plane that includes these three arrows. So this is totally polarized in this direction. And by the way, he doesn't mention this, but the refracted ray is completely polarized in this orientation. There is no in and out of the page polarization of the refracted ray. Okay. Now, what he mentions is that leads to a particular way of determining the refractive index. So let's actually work out the mathematics of this. And this is, I think, one of your homework problems as well. So we'll work through this. So as always, I'm going to draw a vertical line here to create some real estate for myself. So as always, let's call this medium 1. We'll have a refractive index n1 and n2 like that. And so we have, for the law of refraction, n1 sine theta 1. And in that case, sine theta 1 would be sine theta of the incident ray. And that has to be equal to n2 times sine of theta 2, and that would be the angle of the refracted ray. Okay? And also, so this is the law of refraction. And then also the law of reflection says that the incoming ray, the incidence ray, has to have the same angle with respect to a perpendicular as the reflected ray. So this is the law of reflection. And this was Snell's law, or the law of refraction. Okay? Now, also notice that for this particular case, we're going to say that the refracted ray is going to be equal to 90 degrees minus the angle of the reflected ray. That makes it so that the sum of these three, the reflected, the refracted, and this 90 degree add up to 180 degrees. So this is the case, the special case that Mr. Brewster is talking about, special case. Okay? Notice that if we do that, let's plug in this equation. We'll call this equation 1, equation 2, and equation 3. Let's plug in equation 3 into equation 1. So we'll get n1 times sine of theta incident equals n2 sine of, now for theta refracted, I'm going to put 90 minus theta reflected. And now what I'm going to use is a trigonometric identity that you may recall, that sine of 90 minus an angle is equal to cosine of that angle, cosine of the angle of reflection. So I'm left with n1 sine theta incident equals n2 sine theta reflected. Okay? And now what we can do is recognize, using equation 2, that the reflected angle is the same as the incidence angle. So in other words, n1 sine theta incident is equal to n2 cosine of theta incident. Okay, that's using equation 2. And now what I'm going to do is I'm going to cross multiply. So I'm actually going to divide both sides by cosine of theta and divide both sides by n1. And so on the left side, I'll get sine of theta incident over cosine of theta incident equals n2 over n1. And now I'm going to come down here. And notice that the ratio of the sines to the sine of an angle to the cosine of an angle, of course, that is the tangent of the angle. The tangent of the angle of incidence is equal to the ratio n2 over n1. And if n1 happens to be air, it's coming out of air, which has a refractive index of about 1, then, so if n1 is about equal to 1, then we have that n2, the refractive index of the medium, is equal to the tangent of the incidence angle. Okay, so this is an important formula because it provides a way of finding the refractive index of a material by looking at the reflected ray. Namely, when the reflected ray is completely polarized, that is the angle called Brewster's angle, at which when the incidence angle is equal to the Brewster's angle, that is when the reflected ray is completely polarized, and then we can use that to find the refractive index of the glass. Okay, so that's something that you studied in lab this past week. You measured the refractive index of glass by measuring the Brewster's angle, the angle of complete polarization of the reflected ray. Okay, let me say just a couple of other things about this chapter before we move on. So if you look ahead at the next page, he's talking a bit more about polarization of light as it travels through tourmaline. And we talked a bit about that in my last lecture. And then on the next page, he gives more examples as you slowly rotate these, what kind of, how the transmitted light behaves. And then finally, he mentions the following. He says one more word. This is at the end on page 265. He says one more word. When the tourmalines are crossed, the space where they cross each other is black. So that's the case when you have these crossed polarizers. Now suppose when the two plates are crossed that we interpose a third plate of tourmaline between them with its axis oblique to both. A portion of the light transmitted by the first plate will now get through this intermediate one, but after it has gone through, its plane of polarization is changed. It is no longer perpendicular to the axis of the crystal in front, hence it will get through that crystal. Thus, by pure reasoning, we infer that the interposition of a third plate of tourmaline will in part abolish the darkness produced by the perpendicular crossing of the other two plates. So what is he saying? He's saying if we have light that's traveling along an axis, and I'm going to draw these axes like this so we can be precise in our language. And let's suppose that this light is traveling in this direction and it is initially unpolarized. That is, it has both vertical polarization and horizontal polarization. That is polarization along both the x-axis and the y-axis. And now suppose we put a plate of tourmaline in here that is oriented so that it only allows vertically polarized light to get through. That being the case, in this region there is vertically polarized light. And now if we take another sheet of tourmaline and we cross it like this, that is, we have it so that the axis that it allows light through is perpendicular to the axis of plate 1, so this is plate 1 and plate 2, then of course you'll have darkness over here. It will be dark. No light will get through because they are crossed. But here he's saying, what if we do something interesting? We place another piece of tourmaline between them so that it is at a 45-degree angle. He says an oblique angle compared to the previous two. He says in that case what happens is you have this vertically polarized light striking plate number 3, and that in fact is going to change the plane of polarization to a diagonal polarization. It'll be slightly dimmer than the original light because only a portion of that light gets through. It is the part that lies along these axes that are diagonal. So you might think about it this way. If you have let me go back for a moment. So if you have, looking at this head-on, these diagonal slots or slits that would allow light through only diagonal, if the light hitting it is vertically polarized, you can kind of think of that as having a component of it that is parallel to those slits and a component of it that is perpendicular to it. This part right here will be blocked, but the part right here will be transmitted through this diagonally polarized tourmaline sheet, and that is exactly what's happening right here. And now when this diagonally polarized light strikes the tourmaline plate number 2, once again, part of it is parallel and part of it is perpendicular to the orientation of the tourmaline, and the part that is parallel to it will get through, and hence you will have a little bit of horizontally polarized light getting through, and now it is no longer dark, but it is bright. So it's interesting here that by adding a third polarizer in between two cross polarizers, you can actually increase the amount of light that is transmitted through the crossed polarizers. This is going to be an important concept when we get to talking about phenomena like using quarter wave plates and selenite in the next chapter.